Hello, my name is Carter, and this is my group submission for Physics 211 Project 1. I'll be describing the motion of the helicopter in this problem. As defined by the assignment, the helicopter takes off from rest at t equals negative capital T and flies some known horizontal distance d for an unknown amount of time. And its motion is described by this acceleration equation, where this first section is in the x direction and the next is the y direction. So to make sense of this, I graphed both of these portions of the acceleration equation, where x is in red and y is in blue. X is a linear relationship, so it has a positive and decreasing acceleration where it reaches zero acceleration or a constant velocity at t is zero and begins to decrease, so a decreasing velocity. In the y direction, it has a similar behavior, but it decreases much faster and has zero acceleration for a longer period of time in the middle. So it would have a constant velocity for a longer period of time. And just to verify that, to look at the velocity equations for both of these functions, you can integrate the acceleration equations to obtain these, which represent the same. Again, at t is zero, x has no acceleration, so a constant velocity, which is no slope in the velocity equation. And the blue graph, the y direction, similarly, it has a velocity initially, but reaches zero velocity in the middle, and again, speeds up towards the end in the y direction. So that would mean that it would increase its height at the end. So once again, looking at the position, you can integrate the velocity functions to obtain the position. And here at the end, I just added a constant for both of these, which was found using plugging in T4 at where T is capital T. And this would just give you basically, this would set these equations to have position 0, 0 at the same time at negative T. So looking at the Y position, the object increases its height. The helicopter stays at this height for a while and then slowly begins to increase again before it stops at t equals 5. And this height at t equals 5 would represent the delta y, the change in height in this helicopter's motion. For the x, it moves with a relatively constant velocity. It speeds up at the beginning and then reaches this constant velocity and then begins to slow down until at the end of its motion, it has zero velocity, which represents a flat slope in the position graph. So that has been the motion of the helicopter. And next we're going to do some sense making about the problem. Thank you.
For this problem, we are presented with an equation modeling a helicopter for the next Mars rover. With this information, you need to find how much time the helicopter spends in the air and where the helicopter lands. To find the answers to these two questions, you need to find the position equation. But first, you must understand the variables. Beta and alpha are both known constants. Lowercase t stands for time and is a variable. Capital T is unknown but constant. We will solve for this as it will help us tell us the time the helicopter spends in the air. The other two variables from the acceleration equation are x hat and y hat. These are unit vectors that show direction of that part of the equation. X hat is for the x-axis and y hat is for the y-axis. To find the position equation, you need to integrate the acceleration equation. This means you need to integrate acceleration to find velocity and then integrate velocity to find the position equation. These equations are all split into x and y components. With the x component of the position function, you can find distance. You can then plug that into your y component of position to find time. Solving for these variables tells you that time is 2 capital T, 2 because the helicopter begins at negative capital T, which is the square root of 3/2 the horizontal distance over beta. The vertical distance is alpha over 35 beta times the horizontal distance. And distance in the horizontal direction is 2/3 beta capital T squared. These make sense because distance and time are related for the horizontal distance and for the time components. The greater the distance you're traveling, the more time it will take to get there. and the other way around as well. The greater the time it takes to get somewhere, the longer you will be traveling. For the vertical distance, it makes sense because the horizontal distance you will travel will affect the vertical distance you travel. The farther you're going, the higher in elevation you will get. The vertical distance makes sense because the horizontal distance you travel will affect the vertical distance you travel. The farther you're going in horizontal distance, the higher in elevation you will get, and the greater change in height you will experience.
There are similarities between the helicopter motion problem and the problem of a bicycle between the traffic lights in the homework 2. In both problems, the acceleration, velocity, and the distance motion image are similar, and both involve determining the distance traveled by a moving object. Also, in both problems, sense-making about the constants, though they affect results, is also the same, and they all stopped at the start. However, there is a big difference between these two problems. First, the motion of the object in the problem is completely different. The helicopter moves in the X and the Y directions, while the bicycle moves only in the X direction. In addition, in the bicycle problem, the velocity of the bicycle is known and described as a function of time, while in the helicopter motion problem, the acceleration of the helicopter is known and described as a function of time. In addition, in the bicycle problem, the distance between traffic lights is solved, while in the helicopter motion problem, the time spent in the air and the distance before landing are solved. In the bicycle problem, the bicycle starts at t = 0, while in the helicopter motion problem, the helicopter launches from rest at t = -t. Another important difference is the dependence of the mathematical function on different constants. The acceleration function in the helicopter motion problem depends on alpha and beta, while the velocity function in the bicycle problem depends on v. In summary, although both bicycle between traffic lights problem and the helicopter motion problem involve determining the distance traveled by a moving object, they differ in the nature of the motion, the quantity known, and the mathematical functions used.